Up next, in our final talk of the session, we have Ben Rose from Baylor University, who's going to talk to us about investigating weak lensing effects on supernova cosmology.
Okay, thank you. So I'm going to talk to you a little bit about how weak lensing can affect Type 1a supernovae. I want to highlight first off that this work has been done by two of my students, Jenna, who's just got her master's, and Jansen, who's just starting her PhD. So for a quick background, gravitational weak lensing, you have some sort of object that you're looking at. In my world, that's a Type 1a supernova. And it is lensed by the matter along the line of sight. And what's most important in the supernova world is not necessarily the distortion in the shape that is used in weak lensing, but the magnification that is done. And so you can see, this is from a DES survey, that there is some magnification, a shift in the observed magnitude of the supernova because of this sort of foreground mass distribution. So that says, so what do we do with this? This is sort of a random process. It's really hard to know exactly all of the matter between us and a supernova, particularly once you start getting to higher redshift. So there's two sort of things you can do with this. You can either just say, hey, it's noise, and just add it to your noise term, or you can actually say, hey, that's actually probing the growth of structure and start to actually understand more cosmology. And so we've been looking at what both increasing the uncertainties and probing cosmology would look like at above redshift 1. So here's what they've done before. So in the DES cosmology analysis, we used this sort of linear relationship. So as you go higher in redshift, you have more material between you and the supernova. And so you increase your sort of scatter due to this effect. The problem, though, is if you get above redshift 1, particularly by the time you get to 2.5, where Roman is still looking, this becomes the dominant sort of scatter in supernova cosmology. And so there's quite a bit of uncertainty here, such that if this was on the higher side, you would actually, this would be the dominant sort of scatter in our measurements well before redshift 2.5. So we wanted to look at this a little bit more because this was tested and developed and fit to data from SNLS. So a smaller data set, lower redshift. And so we looked at building a sort of simulation of what Roman will see. Using the high latitude time domain survey, using the SNANA software, and most importantly was this sort of lensing map. So we took galaxies from the DC2 from DESC, and then we superimposed and paired up that with a foreground lensing map that was derived from the dark energy survey. And so you can see here on the right, this is our sort of magnification map. So as a result, this was the output of our sims. You can see we've got the typical Roman supernova count with most of the objects above redshift 1. But you can see here on the right, the lensing magnification that we added in as a function of redshift. And so this has the properties that we would expect, that the majority of them are shifted down here, that it's asymmetric and increasing, and that the scatter is increasing with redshift. So this allows us to fit that sort of scatter, that Gaussian scatter there. And we can see that it is still within this uncertainty range, because the uncertainty range is huge. But we see that the linear relationship is not necessarily what we should be using above redshift 1, which is great because now this stays well outside of becoming a dominant scatter and uncertainty in our measurements. And we're working on trying to finalize this up and get this paper out later this year. But of course, the other half is there's actually signal in this. We don't need to just treat this as noise, but it is the growth of structure. It is sigma 8, so similar properties that allows us, that is making this happen. So currently, type 1a supernovae are just looking at the expansion history of the universe, which gives us a great handle on the densities of both matter and dark energy, but it doesn't give us the growth of structure very well. And that is because the growth of structure is that higher order moments is where it shows up in the Hubble diagram. And so there's a method called the method of moments that looks at not just the mean and the scatter, which is what you typically do for linear regression, but also looking at the third, fourth, and even sometimes all the way up to the 8th moment of the distribution. And so your sigma 8 comes in once you start looking at the third and fourth moment. So we do have some initial results. This first was developed in 2014 and tested on some LSST simulations. So you can see here on the very left plot that with just doing the first and second moment, that is your standard sort of linear regression fit, you have no constraining power on the growth of structure on sigma 8. Once you start adding the third moment and looking at these nonlinear components, you are able to start constraining sigma 8. And so we have actually started to look at this and apply this not just to LSST like they did in this original paper, but apply it to Roman. And we do have an initial result. There are some oddities that are happening in this that we are still sort of investigating, but we're hoping to track those down and get that out soon. So that's what I have to say. Weak gravitational lensing becomes a major sort of change. It's one of the unique things that we're going to have to deal with in high redshift supernova cosmology. We've been able to test a few things where it looks like it's not as bad as we once feared that it might be in terms of scattering and noising up our data. And we're looking forward to maybe even expanding the types of cosmology that we're able to constrain with supernovae. Thanks.
All right, thanks, Ben, for the nice talk. We have plenty of time for questions. Okay, let's go to you over here.
Nice talk, Ben. Just want to mention that Zhong Xuzai and myself and Dan Skolnick wrote a paper
Yes, you
on
did.
measuring sigma 8 using weak lensing on supernovae from Roman 2000.
Yes.
So it's a complementary to your approach, so maybe a useful.
It is. We have looked at it,
Comparison.
and we should look at it again as we're trying to debug some of the stuff.
Right, because I think what we found is that there are some fundamental limits where you need actually to have very sophisticated simulations to supplement it. Otherwise, just using the magnification distribution from supernovae will hit a hard limit. Yeah, but very, very exciting, obviously. Thanks.
Over here.
Hi, Ben. I just wanted to ask, are there any other sort of cosmological phenomenon that you would expect to affect the third and fourth moments of the distributions, or is it just sigma 8?
You're asking me to put on my theorist hat. That
Sorry.
is not very good.
The worst hat.
So the standard, so omega matter and omega lambda do affect those, particularly the even moments. Probably the biggest one is just sort of the intrinsic scatter of supernovae. That's a weird one, and we don't fully understand it, so it can have a bunch of different shapes. In terms of cosmological, I'm not sure I know enough I don't think there is much, but I would want to go talk to some theorists who are used to doing the perturbations there.
Okay, so I have kind of a naive question. So is it the combined observations of Rubin and Roman that give you more constraining power of sigma 8? Or which one is?
Yeah, you can. These are just, the left is just using LSST sims, and the right is just using Roman sims.
I see.
But you can combine them and get a better constraint.
Okay.
Yeah.
Okay, cool. All right, any more questions for Ben? Yeah, if not, let's thank Ben and the rest of the speakers in this session.